the theory of relativity. Einstein had to sort of reject the Newtonian physics and come up with this space-time continuum. He completely rewrote the rules. AGI will be when we're able to create new science, new results, new math. When an AGI comes up with a theory of relativity, it has to go beyond what it has been trained on to come up with new paradigms, new science. And that's my definition of AGI.
Martine, I knew you wanted to have Vishal on.
Yeah.
What do you find so remarkable about him and his contributions that inspired this?
Vishal and I actually have very similar backgrounds. We both come from networking. He's a much more accomplished networking guy than I am. But
That's a high bar given you have to vet some field.
But we come
generous.
from, and so we actually view the world in an information theoretic way. It is actually part of networking. And, you know, with all this AI stuff, there's so much work trying to create models that can help us understand how these LLMs work. And in my experience over the last 3 years, the ones that have most impacted my understanding, and I think have been the most predictive, are the ones that Vishal has come up with. He did a previous one that we're going to talk about called Matrix, is it?
Beyond the black box, but yeah.
Beyond the black box.
Matrix
So
is
actually,
yeah.
and we should put this in the notes for this, but like the single best talk I've ever seen on trying to understand how LLMs work is one that Vishal did at MIT, which Hari Balakrishnan pointed me to, and I watched that. So he did that work, and then he's doing more recent work that's actually trying to scope out not only how LLMs reason, but like it has some reflections on humans' reason too. And so I just think he's doing some of the more profound work in trying to understand and come up with models, formal models for how LLMs reason.
Well, just on that note, you said his most recent work helped you change how humans think. Why don't you flesh that out a little bit? How did it sort of?
Well, okay. So can I just try to take a rough sketch at it, and then you just tell me how wrong I am?
Go right ahead.
You know, you're trying to describe how LLMs work, and one thing that you found is that they reduce a very, very complex, multidimensional space into basically a geometric manifold that's a reduced state space. So it's reduced degrees of freedom, but you can actually predict where in the manifold the reasoning can move to. Roughly. So you've reduced the dimensionality of the problem to a geometric manifold, and then you can actually formally specify kind of how far you can reason within that manifold. So and the articulation is that one of the intuitions is that we as humans do the same thing. Is we take this very complex, heavy-tailed stochastic universe and we reduce it to kind of this geometric manifold, and then when we reason, we just move along that manifold.
Yeah, I think you captured it accurately. That's kind of the spirit of the work. Yeah.
Wait, can I just hear it in your words? Because I'm this lay. I'm a VC, so
you're a VC with an H index of what, 60?
True.
Yeah. So ultimately, what all these LLMs are doing, whether the early LLMs or the LLMs that we have today with all sorts of post-training, RLHF, whatever you do, at the end of the day, what they do is they create a distribution for the next token. Right? So given a prompt, these LLMs create a distribution for the next token or the next word, and then they pick something from that distribution using some kind of algorithm to predict the next token, pick it, and then keep going. Now, what happens because of the way we train these LLMs, the architecture of the transformers, and the loss function, the way you put it is right. It sort of reduces the world into these Bayesian manifolds.
Yeah.
And as long as the LLM is going in sort of traversing through these manifolds, it is confident. And it can produce something which makes sense. The moment it sort of veers away from the manifold, then it starts hallucinating and starts spouting nonsense. Confident nonsense, but nonsense.
Yeah.
So it creates these manifolds, and the trick is, the distribution that is produced. You can measure the entropy of the distribution. right? But entropy, the way
Yep.
Shannon described it.
Shannon
And
entropy. Yeah.
Shannon entropy, not thermodynamic entropy. so, so suppose you have a vocabulary of let's say 50,000 different tokens, and you have a distribution, next token distribution over these 50,000 tokens. So let's say the cat sat on the, right? If that is the prompt, then the distribution will have a high probability for mat
Yeah.
or hat or table, and a very low probability of, let's say, ship or whale or something like that, right?
Yeah.
So because of the way it's trained, it has these distributions. Now, the distributions can be low entropy or high entropy.
Yeah.
A high entropy distribution means that there are many different ways that the LLM can go with a high enough probability for all those paths.
Yep.
Low entropy means that there are only a small set of choices for the next token. And the prompts also you can categorize into two kinds of prompts. One prompt is you can say high information entropy.
Yep.
And one prompt is low information entropy.
Yep.
So the way these manifolds work, the LLMs start paying attention to prompts that have high information entropy and low prediction entropy. So what do I mean by that? So when I say I'm going out for dinner, right? So when I say I'm going out for dinner, that phrase the LLMs have been trained. They've seen it a lot, and there are many different directions I can go with it. I can say I'm going for dinner tonight. I'm going for dinner to McDonald's, or I'm going to dinner blah blah blah. There are many different. But when I say I'm going to dinner with Martin Casado, the LLM, now this is information rich. This is sort of a rare phrase. And now the sort of realm of possibilities reduces, because Martin is only going to take me to Michelin star restaurants. I'm not going to go to a McDonald's. You get what I'm saying. The moment you add more context, you make the prompt information rich, the prediction entropy reduces. And another example that I often
but just quickly, but what is your takeaway? What is your implication on that? Which is, of course, as your so you're sorry, I forgot how you described it, but so the more precise you are, the more tokens you are, I presume the less options you have for the next token. Is that correct or not correct?
Yeah, essentially.
So you're reducing it to like a very specific state space when it comes to confidence in an answer. And this is kind of a manifold that you can go on. And then, do you have kind of a conclusion of what that means for systems or what that means for reasoning? Or is it just a nice way to articulate the bounds of LLMs?
No, there is something, I don't know if I should say profound, but there is something about it which tells what these LLMs can or cannot do. Right? So one of the examples that I often tell is, suppose I ask you what is 769 times 1025. You have no idea. You can have some vague idea given the two numbers, right? And so in your mind, the next token distribution of the answer is going to be diffuse, right? You don't know. You have maybe a vague guess. If you are mathematically very good, maybe your guess is more precise, but it's still going to be diffuse, and it's not going to be the correct answer. But if you say, can I write it down and do it the way we have learned multiplication tables, now you know exactly what to do the next step, right? You write 769 and then 1025, and then you know exactly. So at each stage of that process, your prediction entropy is very low. You know exactly what to do because you have been taught this algorithm. And by invoking this algorithm, saying, okay, I'm not going to just guess the answer, but I'm going to do it step by step. then your prediction and entropy reduces. And you can arrive at an answer which you're confident of and which is correct. And the LLMs are pretty much the same way. That's why chain of thought works.